right, let's get started. Well, hello everyone. Thank you for joining us for the first EPSP Connect seminar of this season. The purpose of this series is to bring the community together, and to help establish connections between people who might not be able to interact with others in a different setting. So we're very happy to have you here. And before we kind of move on to the talk, I'd just like to thank all the EPSP Connect team. Some of us are here, some of us kind of work behind the scenes or lead other sessions in different months. So just thank you to everyone who helps coordinate, with speakers, prepare the flyers, take care of the Zoom, etc. Joining me today as a co-host is Tyler Doan, who will help us with the Q&A session. So Tyler, what's the plan for that?
Yeah, so for the Q&A, if you have questions throughout the talk, please go ahead and write them into the chat in the Zoom. If you prefer, though, we can also unmute you at the end of the presentation. And we are also live streaming this on YouTube, and we will keep an eye on the YouTube over there for questions. So please don't hesitate to write out your questions as they come to you.
All right, thanks. So our speaker today is Dr. Chenge An from Tsinghua University. I'm very happy to be hosting him. I haven't seen Chenge in probably 5 years now. Dr. An completed his PhD in Tsinghua University and worked as a visiting scholar in the US and Canada. Specifically, he worked at the University of Illinois, Urbana-Champaign, and at the University of British Columbia. Dr. An's research focuses on morphodynamic modeling of alluvial and bedrock rivers at different scales. And today he'll talk about post-earthquake river degradation due to complex interaction of weirs, sediment supply, and sediment mining. So Chenge, please take it away.
Thank you, Roberto, for the introduction. And thank you, Tyler and Shashank, for organizing this presentation, this lecture. I'm very, very glad to have a chance to present my recent work in the AGU EPSP Connects. And today, the title of my presentation is Foreland River Degradation After Massive Earthquake, Effects of Weirs, Sediment Supply, and Sediment Mining. Yes, and we all know that river degradation has been a global problem in the last few decades. And in this map, it shows the river degradation in the rivers worldwide, including some of the largest rivers around the world, like the Yangtze River in East Asia, and the River Rhine in the Europe, and the Mississippi River in the North America. And for example, for the River Rhine, it has been degrading for the past century, and maximum degradation reported is more than 10 meters. And for the Yangtze River, since the closure of the Three Gorges Dam, which is a very large dam, in 2003, very significant river degradation happened in the downstream, with maximum degradation of 20 meters reported in 15 years after the closure of the dam. And the river degradation has several very negative consequences, including the damaging of the shallow water habitats, the threatening of the river infrastructures like the bridge, the pipelines, and other infrastructures. And also it can induce bank instability and bank failure. And the engineers have thinking about and proposed different engineering measures to inhibit the river degradation. And one of the very famous practice is the artificial gravel feed in the River Rhine. And the left photo shows in the shape a lot of gravel is fed artificially in the river to reduce the river degradation. And now let's turn to the Longmen Mountains in China, which is the focus of our work today. And this map shows the location of the Longmen Mountains, which is in the southwestern China. And the Longmen Mountain fault zone is one of the largest seismic zones in the world. And this map shows the spatial distribution of the earthquakes in this region in recent years. And because of this earthquake, especially after the 2008 Wenchuan earthquake, severe Foreland river degradation has been reported in the Foreland river basins of the Longmen Mountain. And in the map, in the right map, it shows the river degradation in the Foreland basin of the Longmen Mountains, and the color of the dots represent the degradation depth of each local site. And it can be seen that a maximum of 30 meters can be seen in several river reaches. And among these Foreland rivers, the Xijing River experienced the largest degradation, and which had a maximum degradation of 20 meters in 7 years and 30 meters in 14 years. And in these photos, we can see that very large degradation is observed near the bridges and also near the weirs. And for example, in the bridges, the yellow dashed line shows the elevation of the original bed, and because of the degradation, a large part of the bridge pier was exposed. In 2012, 11 meters of bridge pier was exposed, and also in 2015, the bed degradation was at large at 22 meters and 24 meters in 2021. And in the middle figure, it shows that overall picture of the degradation reach of the river, which we can see that the river morphology and the ecological habitat is totally destroyed. And in the upper right figure, it shows the river long profiles at different years from 2008 and 2022. And it also showed very large degradation at many sections, at many reaches along the river. So several different hypotheses have been proposed to explain the dramatic degradation of this Xijing River. And the first hypothesis is about the supply of fine sediment. In many previous flume experiments, the experiment showed the magic sand effect, which is the sand supply can significantly increase the gravel transport rate. And this can further lead to bed degradation and reduce the channel slope. And in the left figure shows the flume experiment of Wilcock et al. And we can see that with the increase of the sand fraction on bed surface from the open circle to the solid triangle, the gravel transport rate increased by about 2 orders of magnitude under the same flow discharge. And in the middle and the right figures show the most recent flume experiment of Hassan et al. And they show that with the input of sand into the flume, into a flume of gravel bed, immediately after sand supply, a spike in gravel transport shows, and after that, a reduction in the bed slope happens consistently and continuously. And when we come to the Longmen Mountains, a large number of landslides and debris flows occurs after the Wenchuan earthquake. And this satellite image shows the landscape erosion after the earthquake. And as a consequence, a huge amount of fine sediment enters into the Chenge River, as shown in these photos. And in the photos, we can see a lot of fine sediment on the riverbed, which was not there before the earthquake. And this sediment can play a big role in the river adjustment after the earthquake. The second hypothesis about river degradation in the Chenge River is related with in-channel weirs. And people had found that the in-channel weirs can break the sediment connectivity in a river, and as a result, upstream of the weir, sediment deposit due to the backwater effect, and downstream the weir, there is bed degradation and a reduction of the bed slope. And for the Chenge River, several in-channel weirs exist along the Foreland ridge. And it is observed that the degradation is the most evident immediately downstream of the weirs. And in this map, there shows 6 major weirs along the Foreland ridge of the Chenge River. And in the table, it shows the drop height of each weir at different time. And here, the drop height of a weir is defined as the elevation difference between the weir crest and the downstream riverbed. It can be seen that the drop height can be as large as 30 meters after bed degradation. And the third hypothesis relating with the bed degradation in the Chenge River is sediment mining. And we all know that the sediment mining can lead to significant changes in the river morphology. And for the Chenge River, large sediment mining had occurred after the earthquake, and the reason is the large demand of the construction materials for the post-earthquake construction. And these photos are the aerial photo that we took in July this year. And in the left upper left photo, it shows the dredging machines working on the channel, basically taking the sediment from the river. And in the lower left panel of this figure, it shows the factory on the channel and the river bank, which sieves the sediment from the river channel. And in the bottom of the photo, we can see the truck is taking the sediment from the river bank into the factory. And in the red panel, it shows several sediment piles positioned along the river bank, which store the sediment from the river channel. So here we propose our research questions based on the previous hypothesis. The first question is, what are the combined effects of weirs, sediment supply, and sediment mining on Foreland River degradation? And the second question is that among these 3 factors, which one played the key role in the case of the Chenge River after the winter earthquake? To give an answer to answer the above research questions, we use a 1D morphodynamic model to do the simulations for the Chenge River. And first, we explain the numeric model that we use. The model we use has 3 major parts, which is the flow hydraulic part, the sediment transport part, and the sediment conservation part. And for the flow hydraulic part, we use both the shallow water equation and the backwater equation. The backwater equation is a simplified version of the shallow water equation under quasi-static flow conditions. For the sediment mass conservation, we apply the action equation with an active layer formulation. In the active layer formulation, the riverbed is divided into an upper active layer and a lower substrate. The active layer is the part of the bed which can interact directly with the sediment load, and it can also exchange with the substrate during the river aggregation and degradation. We further divide the substrate into a number of sublayers to store the vertical stratigraphy of the substrate. And for the sediment transport, we use the Wilcox and Crowe relation to do the calculation. In this slide shows the equations of the Wilcox and Crowe relation. And the reason why we use this relation is simple, because it is the first bed load relation that can incorporate the magic sand effect. This equation in the bottom shows the magic sand function in the Wilcox-Crowe relation, and this figure in the upper right part of the slide shows how this function works. With the increase of sand content on the bed, the reference shear stress or the critical shear stress of the sediment transport reduces exponentially. That means that with more sand on the bed, there will be a larger gravel mobility. And because we want to study how the fine sediment affect the bed degradation, this magic sand function is important in our model. And the prototype of our simulation is the Foreland ridge of the Sheeting River. And the length of our computational ridge is 50 kilometers, with upstream end at the mountain exit and the downstream end at the river confluence. In our model, we simplified the flow hydrograph into a constant flow discharge using the concept of a flat intermittency factor. And the figure in the upper left of the slide shows the concept of the flat intermittency factor. First, we simplified a realistic hydrograph into a long and low flow discharge and a short flat discharge. We further neglect the low flow discharge with the consideration that it is mostly morphodynamic inactive, and therefore we use the constant flat discharge in our calculation. We apply a discharge of 1,800 cubic meters per second, which is close to the discharge of a 10-year flood. And we apply a flat intermittency factor of 0.03, which means that the river is in flood and morphodynamically active in 11 days of a year. And we apply a channel width of 300 meters. And for the sediment supply before the earthquake, we consider only gravel supply, and as reported by Fan et al. In 2016. And for the initial substrate, the grain size distribution of the initial substrate, we apply the same grain size distribution as the gravel supply. And in this figure, the blue line shows the grain size distribution of the gravel bed. And with this gravel supply and the flow discharge, we can calculate the channel equilibrium before the earthquake. And in this equilibrium, the slope is 0.52%. And in this figure, the black dashed line shows the simulated grain size distribution of the bed surface in equilibrium with a geometric mean grain size of about 30 millimeters. And when we compared our simulated values with the measured values before the earthquake, our simulated values is about at the lower bound of the measured range, which corresponds to the Foreland ridge, lower Foreland ridge of the river. So after we validate our model with the field data, we start to study the three different factors that we proposed before. The first factor that we want to study is the magic sand effect, or the effect of the fine sediment supply into the channel. As we have explained, in the pre-earthquake condition, only gravel is supplied into the channel. And for the post-earthquake condition, we consider two scenarios. In the first scenario, we consider the gravel augmentation, in which we doubled the gravel supply before the earthquake, but with no sand supply. And in the second scenario, we fix the gravel supply at the pre-earthquake condition, and we increase the sand supply from 0 to the value which is same as the gravel supply. And in the figure, the blue line and the red line shows the green side distribution of the gravel feed and sand feed respectively. And here is the result of the first scenario, which is the augmentation of gravel supply. And the results show that after 20 years, the bed degradation occurs from the upstream end and propagate to the downstream. The bed surface becomes slightly finer with the geometric mean grain side adjust in form of downstream migrating sorting wave. However, in the scenario of sand augmentation, we see bed degradation from the upstream end, and also the bed surface fine rapidly due to the supply of fine sediment. And also within 1 year, with the increase of the sand supply, we can see the bed surface, on the bed surface, the sand fraction increased from 0% to about 20% rapidly. And with this increase of the sand content on the bed surface, the gravel transport rate increased significantly by more than 100%, even though the gravel supply rate is fixed. And this is the result of the magic sand effect. And because of the increase in both the gravel transport rate and the sand transport rate, in a longer time of 20 years, we see more significant bed degradation from the upstream to downstream. But when we compare this bed degradation, the simulated bed degradation with the observation, it is still much lower than the observation of 20 meters in 7 years. And then we start to think about, if we increase the sand supply rate to a larger value, will we see an even more intensive bed degradation? To explore this, to answer this question, we still fix the gravel supply rate, but we vary the sand supply rate with different factors from 1/4 to 3. And the simulation we show in the last slide correspond to the RSG equal to 1, which is the gravel supply rate equal the sand supply rate. And also we define a reference time scale of bed degradation, TR. Here, TR is the time required for bed degradation depth of dirt dB to occur at a distance of X. And this slide shows the reference time scale correspond to both 2 meter degradation and 20 meter degradation. And we found that the results are not very sensitive to the sand supply rate, especially with the 2 meter degradation scenario. The different lines are very close with each other. And for the 20-meter degradation scenarios, the case of RSG equals to 1 shows the most rapid degradation. And even though at least 50 years are required for a 20-meter of degradation to occur, which is at this point, which that it is at the most upstream part for 20-meter degradation to happen, TR is about 50 years. So which is still much slower than the observation. Then we start to add a bit more effect, which is the in-channel weir effect. We combine the weir effect with the magic sand effect to see what will happen. And here, when we incorporate the in-channel weir effect, we first consider pre-earthquake condition, which is only gravel. We first see when there's no fine sediment supply, but only a single weir, what will happen? And we put a weir of 5-meter head at a location of 20 kilometers from the upstream, end. And we can see that here is the place of the weir. We can see that downstream of the weir bed inside this for about 5 meters in 20 years, and with about the same deposition in the upstream. And for the bed surface, the downstream bed coarsens in the first 2 years by about 50%, but then recovers gradually afterward to the initial value. And then we combine the weir effect with the magic sand effect. Here we consider both the sand augmentation and also a weir of 5-meter head at a location of 20 kilometers. And we see that a 30-meter incision, bed incision happened at the inlet, and a 5-meter bed incision happened downstream of the weir. And the entire weir bed finds rapidly after 1 year. It means that the fine sediment can pass the weir after 1 year to the downstream. And when coupling the effect of weir and magic sand, we find interestingly that the two effects can enhance each other. This figure shows how the coupling effect works. The blue area shows the bed degradation induced only by the effect of weir. That is, we only consider there's only a weir in the channel, but no fine sediment supply. And the yellow area shows the bed degradation induced only by the supply of sand without weir. And the red line shows the bed degradation when we consider both the effect of weir and the effect of fine sediment supply. And we see that when the weir and the horizontal axis shows the location of the weir, and we find that when the weir location is smaller than 15 kilometers, that is the location of the weir and the location of the fine sediment supply is smaller than 15 kilometers, the coupling effect of the two factors is larger than the sum of the two factors independently. And why the coupling effect is more than the sum of the two independent factors? And we show this in terms of the fractional sediment transport rate. In the left figure, it shows the gravel transport rate downstream of the weir, with the black line shows the case without weir, and the red line shows the case with the weir. And we can see that the transport rate of the gravel is reduced by more than 40% when there is weir. And in the middle figure shows the transport rate of sand, and we can see that after less than 1 year, the sediment transport rate with and without weir is about the same downstream of the weir. And the time of 0.6 year is correspond to the time that the sediment can bypass the weir. And it means that the weir can, after 6.6 years, the weir can still trap the gravel, but it releases the sand the sand flags totally. And when we have a look at the bed surface downstream, we can see that the sand content increased by 50% when there is a weir. That means that when a weir is coupled with the fine sediment supply, it can enhance the magic sand effect in the downstream. And in the third part, we consider all the three factors with sediment mining, the weir, and the magic sand. The information of the sediment mining is estimated from the satellite images. We first divide the study ridge into 5 sub-ridges with location shown in the table below. And for each sub-ridge, we determine from the satellite images to tell whether there is sediment mining for a given time period. And for all the sub-ridges with mining, we specify a constant mining rate from of different values. And in the right figure, it shows the location that we detected from the satellite images of the mining sites. And in this part, we further consider the existence of cascading weirs instead of the single weir that we considered in the previous section. And we consider 6 weirs, and we also consider when the weir, we also remove 2 of the 6 weirs when the weir is reported to be failed in 2015. And this slide shows that when we consider all the 3 factors, the comparison between the simulated and the observed drop height at each weir. We have the measured values at 2015 and 2015 and 2022. And the left figure shows the path shows the scenario without mining, and we can see that the simulated drop height is significantly estimated compared with the observed values. But when we apply a mining rate of 1.2 meter per year, the simulation and observation generally agree. And we test different values of mining rate, and we find that the mining rate of 1.2 meter per year is about the value with the smallest mean square error. And this slide shows the temporal variation of drop height at weir 3. At this place, we have continuously observation of the drop height from 2008 to 2020. And we find that because this weir shows the largest degradation among all the 6 weirs observed in the field. And we find that our simulation agrees with observation when the mining rate is in the range of 1.2 to 2 meter per year. And we also compare the simulated bed surface grain size distribution at the weirs. And the observed grain size distributions are obtained from the Wallman method, which is cut at 8 millimeter here. And the simulated grain size distribution agrees with observation at 95% significance level with the KS test. And this slide shows that when we consider all the three factors, the spatial temporal distribution of the bed degradation when a mining rate of 1.2 millimeter per year is applied, we find that the largest degradation occurs downstream of the weir 3 at first, and then with when the weir 5 is constructed, the largest degradation occurs at weir 5, and when it failed in 2017, the largest degradation, the location of largest degradation migrate upstream to weir 4, and when weir 4 was failed, it migrated to weir 3 again. And the reason that the largest degradation happened at weir 3, 4, and 5 is because of the large distance from this weir to weir 6. And we also observe evident aggradation upstream of weir 6 due to the large distance, because from weir 6 to the weir upstream before its failure in 2013. And in the end, we give our conclusions. The first conclusion is the in-channel weir and the fine sediment supply can lead to bed degradation. But in the case of the Shooting River, the main contributor is the sediment mining. And the second conclusion is that the weirs can enhance the magic sand effect because it can preferentially trap gravel and deliver sand downstream. And three, the third conclusion is, even though the weirs is not the main contributor of the bed degradation in the Shooting River, the location of the weirs still determines the distribution of the bed degradation. With the largest degradation happens in the weir with the largest distance between from the next weir in the downstream. And the details of this work can be referred to the following two papers. The first is published in 2019 on geomorphology, in which we discussed mainly about the magic sand effect on the bed degradation. And in the second paper, we discussed the combined effect of all the three factors. And this manuscript is just accepted by WR today. And in the end, I want to say thank you to all the contributors. They are the PhD student Yongpeng Lin from Tsinghua University. He is the first author of the second paper in the last slide. And Professor Chenge An from Wuhan University, Professor Nie Ruihua from Sichuan University, Professor Gary Parker from UIUC, and Professor Marwan Hassan from UBC, Dr. Matt Depiga from University of South Carolina, Professor Fan Niannian from Sichuan University, and Professor Xu Dongfu from Tsinghua University. And here I finish my presentation. Thank you for listening, and discussion welcome.
Excellent. Thank you so much for that talk. If a reminder to folks, if you do have some questions, please go ahead and write them out in the chat, and we will read them off. If you prefer to ask it yourself, we can unmute you and you can ask it yourself. We do have a question already in the chat, which is, thank you for your interesting talk. Just curious, given landslide input in association with earthquakes, do some areas of the world experience a pattern of major aggradation rather than degradation? And there's a follow-up question, which is, how does sea level rise influence the aggradation and degradation pattern?
Yes, this question is very interesting question. And actually, in the river that we studied, it shows both aggradation and degradation. And let's go back to the map. So here we started the foreland reach of the river, which experienced very significant bed degradation. But actually in the valley reach of the river, immediately downstream, immediately after the earthquake, very significant bed degradation was reported because of the input of the landslide and the rock failure and the slope erosion. So I think so. At the answer of the question, the both aggradation and degradation can happen after an earthquake, and it can even happen in one river at different reaches. And also, how does the sea level rise influence the pattern? I think here, in this case, the sea level rise does not play a role because the reach is very far from the sea. I think it's more than 1,000 kilometers from the sea. So maybe it will take a very, very long time for the sea level rise to influence on this part. But if the river is not that far from the coast, maybe the sea level rise will play some role.
All right, hopefully that answers the first question. We've got a second one from Shashank. Thanks for the nice talk. I'm curious about the last part on cascading effect of weirs. What is the reason behind the largest degradation occurring based on the distance from last downstream weir?
Yes, very good question. I just go too fast at that part. So let's go to the figure. So actually, the main point here is that the weir downstream plays a role at the base level control for the ridge upstream. So when there is a weir in the downstream, the bed cannot be degraded at this part, and it mainly actually aggregated. So when the next weir is very close to the upstream weir, that means the base level is controlled at this part, and even though there is some adjustment in the bed slope, the degradation depth will not be very large. But if the weir downstream is very far, it means the base level control is far from the upstream. So immediately downstream the upstream weir, very large degradation can happen.
If anybody has any more questions, go ahead and put them in the chat.
I've got one. If nothing pops up, I'll go ahead and ask it. I'm curious about the procedure followed, to do some of the experiments. When you presented the Wilka-Crowe formulation, you had an FS for, I guess it's the fraction of sand and maybe in the substrate or the surface. I don't remember. So maybe
it's the content on the bed surface.
Bed surface. Okay. And then for the experiments, is that added before the experiments, or that's fed into the flume?
Let me see. I cannot remember very clearly in the experiment of Wilcox, but in the experiment of Hassan, because I participate in that experiment, I can explain what we did in that experiment. So here, in the middle and the right figures, what we do is that we start the experiment with only gravel supply and gravel bed, and we run the experiment into equilibrium. and then we start to feed the sediment from the upstream. In different cases, in some cases we feed both gravel and sand, and in some cases we feed only sand and we stop the gravel. But in most of the cases, as soon as we feed sand at the upstream, there will be a spike in gravel transport in downstream because the sediment transport rate is measured at the downstream of the fluid. So basically, the fine sediment transport very fast on the bed surface.
And then you had a kind of a follow-up slide on this effect in terms of the critical shear stress. Does that mean that a very little amount of sand can drastically get rid of an armoring layer?
Yes. So here you can see in the experiment of Wilcox and Crow, the maximum content on the bed surface is about 30%. So you can see that when the bed surface is about 10% of sand, the reference shear stress reduced from 0.035 to 0.025 very significantly. But then later, after when the sand fraction is more than 10 and when you increase it more, the reduction of the reference shear stress is gradual. And after 30%, it's almost constant. But in the experiment of Wilcox and Crow, they do not put even more sand. But in a recent experiment of Elizabeth Dingle, when they have a sand fraction on bed surface being as much as 80 and 90%, they found that gradually the mobility of the gravel will reduce because when there is enough sand on the bed, it can gradually bury the gravel, so it can inhibit the mobility of the gravel. But as you asked, your question is, you also asked whether it breaks the armor layer, right?
Yeah, that's
I'm
the
not
question.
sure.
I'm just thinking, sand comes into the system from any source, and is that enough to break an armor layer?
I'm not sure. There are several hypotheses about how this magic sand functions to mobilize the gravel. So one of the hypotheses is that because it smooths the riverbed, so that the near-bed flow velocity can be increased a lot.
Okay.
So I think the break of the armor layer maybe is a result, not a reason for the magic sand effect. This is my idea.
Okay. All right. I don't know if we have any more questions. If not, Tyler, you can share.
Yeah, and also in our experiment in UBC, when you put a small amount of sand into the bed, you can see very intensive transport of the gravel.
Nice. Thanks.
I don't think we have any more questions in the chat, so I think we're about ready to wrap up. But before we go, I just want to remind folks that next month on October 18th, we have another EPSP Connects event. This will be a presentation by Evan Detier from Occidental College. The title of that is The Global Footprint of a 21st Century Mining Boom in Rivers, Changes to Landscapes and Rivers Across the Tropics, excuse me. So keep an eye on your listservs and social media. We will post details about that there. But thank you, Chenge, again for an excellent talk.
Thank you.
And we will see you all in a month.
Thank you all. Thanks.
Thank you. Bye-bye.